Hey everyone, today we are going to go over stoichiometry. Stoichiometry is a very important part of chemistry, and it's going to involve a lot of calculations. It's going to involve the combination of chemical reactions as well as your balanced chemical equations. So let's go ahead and get started. So what is stoichiometry? The first thing that we need to think about is when we're looking at chemical reactions, does the equation keep track of the number of moles or the mass? And if you're thinking about it, so let's look at it in terms of like, say I had H2 plus O2 yields H2O. And when I go ahead and balance that, I get 2H2 plus O2 yields 2H2O. So does that mean that 2 grams of hydrogen gas with 1 gram of oxygen gas will produce 2 grams of water? Or does it mean 2 moles of hydrogen gas plus 1 mole of oxygen gas produces 2 moles of water? It definitely means the second. So what stoichiometry is stoichiometry keeps track of the quantitative relationships between reactants and products in chemical reactions. Now, if we're given the amount of either starting material or product, we can determine the other quantities. So if I say I start with 52 grams of hydrogen gas, how many grams of water do I produce? You would be able to figure that out. If I said I started with 4 moles of hydrogen gas, how many moles of water would I produce? Some of you might already be able to look at that and say, well, if you had 2 moles of hydrogen gas, I'm going to produce 2 moles of water. So if I have 4 moles of hydrogen gas, I'm going to produce 4 moles of water. Some of you are able to do that. Some of you aren't yet, and that's okay. That's what this unit is about, is working on that. So when we're looking at this, when we're looking at those numbers, these coefficients in front, the 2, the one that's not written, and the 2 here, that tells us the mole ratio. The mole ratio is the proportions in which substances are going to combine or form. So in this case, I have a 2 to 1 to 2 ratio, or 2 moles of H2 to 1 mole of O2 to 2 moles of H2O. So that's the baseline of stoichiometry, is comparing moles of something. So if I'm looking at the reaction between nitrogen gas and hydrogen gas to produce ammonium, I'm going to react 1 mole of nitrogen with 3 moles of hydrogen gas to produce 2 moles of ammonia. So my nitrogen to hydrogen mole ratio is 1 to 3, or 1 mole of N2 to 3 moles of H2. Now in the end, that ends up giving me my conversion factor. So I can write 1 mole of N2 over 3 moles of H2. And those are two things that are equal to each other. So that's considered a conversion factor. So if we're looking at these two different chemical equations, we have calcium chloride reacts with sodium oxalate to produce calcium oxalate and sodium chloride. And we have a 1 to 1 to 1 to 2 ratio there. And then in the next equation, we have 3 moles of calcium chloride reacts with 2 moles of sodium phosphate to produce 1 mole of calcium phosphate and 6 moles of sodium chloride. Now, this reaction is the actual reaction that's used in making human bones. So the coefficients tell us the ratio of the reactants to products, molecules, volume, or moles. So this also could be molecules. So 3 formula units of calcium chloride react with 2 formula units of sodium phosphate to produce 1 formula unit of calcium phosphate and 6 formula units of sodium chloride. You could look at it in terms of that, or 3 liters of calcium chloride react with 2 liters of sodium phosphate to produce 1 liter of calcium phosphate and 6 liters of NaCl. The only problem with that is we're not going to use liters here because we're only using liters if we're dealing with gas. So that wouldn't apply for this reaction, but I use that as an example as if these were moles of gas that we're dealing with. But again, the volume is only in terms of moles of gas specifically. Now, when we look at these ratios, we think about it in terms of moles, okay? So that's going to, again, give us our conversion factor. So in this case, like say I wanted to go from calcium chloride to calcium phosphate. Well, calcium chloride, if I'm going from calcium chloride, I'm going to put that on the bottom, 3 moles of calcium chloride, and going to calcium phosphate, well, 3 moles of calcium chloride are going to produce 1 mole of calcium phosphate. Okay, so that's going to be your mole ratio conversion factor when you're doing your conversions. So let's look at this. And this is going to be real quick. We have magnesium solid reacts with 2 hydrochloric acid to produce magnesium chloride and hydrogen gas. So if 2 moles of hydrochloric acid react, how many moles of H2 are obtained or are produced in the end? So for every 2 moles of HCl, I have 1 mole of H2. Okay. How many moles of magnesium will react with 2 moles of hydrochloric acid? Well, for every 2 moles of hydrochloric acid, I need 1 mole of magnesium. Okay. If 4 moles of hydrochloric acid react, how many moles of each product are produced? Well, for every 2, I get 1. So 4 moles of hydrochloric acid equals 2 moles of magnesium chloride and 2 moles of H2. Now there's an easier way to do this, or a mathematical way to do this. So if I look at that, I have for every 4 moles of hydrochloric acid, that's my given that I'm starting with. And I'm going to multiply by my conversion factor, So when I do that, I'm going to put moles of hydrochloric acid on the bottom, and I'm going to put moles of magnesium chloride on the top. Well, for every 2 moles of hydrochloric acid, I have 1 mole of magnesium chloride. So my moles of hydrochloric acid cancel. 4 times 1 divided by 2 ends up giving me 2 moles of magnesium chloride. Now, many of you are thinking, I can just do that in my head. Well, of course you can. I mean, we're going to start small, right? We're going to start at a very small level, and then we're going to build ourselves up, okay? So let's move on and discuss how to solve stoichiometry problems. The first thing is you need to write your balanced chemical equation. That's the very first thing. Cross off words like sufficient, enough, and etc. So, or sufficient, enough, or whatever, excess, whatever you're dealing with. Words that don't really matter and don't affect the mathematical portion of this question, you can just go ahead and cross those out. They're not important, and they end up becoming distractors for you when you're doing the problem. So I'll give you an example of that in just a little bit. Step 3, use dimensional analysis to fill in units to cancel. Okay, so what you're going to do is you're going to use conversion factors here. So you're using conversion factors. And remember, conversion factors are things that are equal to each other. So your numerator and denominator are 2 things that are equal to each other or equivalent to each other. Use coefficients to balance the equation as a conversion factor. Okay. So when we're doing a mole-to-mole problem is always going to be one step. And what you're going to do when you're going from moles to moles, you're going to use your balanced equation, and you're going to use your mole ratio. Okay, so this is called your mole ratio, and you get it from your balanced chemical equation. Notice in this case, when you're going from, say we're doing moles A, and I'm going to moles of B. I'm going to put moles of my given on the bottom, so moles of A on the bottom, moles of my new substance on top. Now the number that's going to go here is going to be based on your balanced chemical equation, your coefficient, okay? So let's look at this as an example. And again, we have the reaction of nitrogen reacts with hydrogen to produce ammonia. So if we have 2 moles of N2 reacting with sufficient H2, sufficient meaning I have more than enough hydrogen, how many moles of NH3 will be produced? Well, let's look at what we can kind of underline to be the most important things. So we have, so this is our given. Our given is 2 moles of N2. Okay, so cross things out. Reacting with sufficient H2. How many moles of NH3? And so that's going to be your question. Okay, that's going to be your question, what you're looking for in your answer. So we write our given first. Okay, we write our given first is 2.00 moles of N2. And we're going to multiply by our conversion factor. Our conversion factor, remember, is our mole ratio from our balanced equation. I put moles N2, moles of my given on the bottom, moles of what I'm going to on the top, and I'm going to NH3. So I'm going to look at my balanced equation. For every 2 moles of NH3, I have 3 moles of N2. So I'm going to do 2 times 2 divided by 3. So I'm going to cancel moles and 2. I get 4 divided by 3 is going to end up being 1.3 moles. And 1.33 if we wanted to look at it in terms of significant figures. Okay? And that is my answer. Okay? 4 divided by 3. Moving on to our next situation, we have, this would be a water treatment example, something that we would use in our water districts to treat water, or when we're looking at water at home. We have hard water and we add carbon, add carbon trioxide, okay, to the calcium to produce calcium carbonate and remove that calcium from your hard water. Okay, so in this case, we have 6 moles of calcium. So we have 6 moles of calcium. This is my given. Reacting with sufficient, so plenty, of CO3. So the CO3 is not going to control the reaction. How many moles of CaCO3, calcium carbonate, will be produced? Okay, so I'm going to start with my given. My given is 6.00 moles of calcium. And I'm going to multiply by my mole ratio. Moles of my given go on the bottom. Moles of my question, or what I'm going to, go on the top, and I'm going to look at my balanced equation. So I have a 1 in front of my calcium, and I have a 2 in front of calcium carbonate. So 6 times 2 divided by 1, make sure moles calcium cancel, and I end with moles calcium carbonate. I end up getting 12.0 moles of calcium carbonate. Okay. So if I have another situation where I'm looking at 6 moles of H2 reacted with excess nitrogen. So 6 moles of H2, that's what my given is, reacted with excess. Excess is another one of those words that it just means extra. It means that there's more than enough. It's like saying there's excess oxygen in the air. There's more than enough oxygen to react in a reaction. So usually that's in excess. Okay, and we'll talk about what that means a little bit more. Like, what if you limit something? So really what's limiting the reaction here is your hydrogen gas. We'll talk about that more next week. But how many moles of ammonia, so you're going to box the ammonia, would be produced? Well, I've got moles of H2. I'm going to moles of ammonia, so moles of my given on the bottom, moles of my wanted value on top. So I have, for every 2 moles there, I have 3 moles here. Moles H2 cancel. 6 divided by 3 is 2 times 2 is 4. So I have 4.00 moles of NH3. Okay, now what if I want to go moles to mass? Well, for a mole to mass problem, I'm always going to have 2 steps. If any quantities are given in grams, those have to be converted to moles first. If you want to end with grams, you have to go mole to mole and then go to mass. So what you're going to be doing is you would either start, if this is your given, okay, you would start with mass and you would convert with your molar mass. So mass to moles, and then you use this mole conversion, your mole ratio, and you end at moles. So each arrow you see is how many conversions you have. So if I'm going moles to mass, I'm going, so say I'm going moles to mass. Say I started here. This is my starting point, okay? If my starting point is at moles, okay, that's my starting point. And I'm going to mass of B. I'm going from moles of A to mass of B. I have to go through moles of B. That's like my mole tunnel. It's like my central station, okay? Grand Central Station, you have to go through it. So I'm going to multiply by my mole ratio here, and then I'm going to go from moles of B to mass of B by multiplying by my molar mass, okay? So let's look at a couple of practice problems for that. Okay, if the problem asks for grams, multiply by the molar mass, and then asks for grams, you're going to multiply by the mole ratio, and then you're going to multiply by the molar mass in the last step. So how many grams of carbon dioxide are formed when 1.65 moles of propane burns in excess of oxygen gas? The other product is water. So the first thing that you have to do is you have to write your balanced equation. C3H8 reacts with O2 to produce CO2 plus H2O. So I'm going to see right here that I have 3 carbons on that side. I'm going to put a 3 there. I have 8 hydrogens. 4 times 2 is going to give me 8. I am balancing this very quickly because it's just a review from previous lesson. 3 times 2 is 6 oxygens plus 4 times 1. So 6 plus 4 is 10. 10 divided by 2 is 5. 5 times 2 gives me 10. So I can just do a real quick check of my carbons, hydrogens, and oxygens on both sides. My carbons, I have 3 on this side, 3 on the product side. My hydrogens, I have 8 on my reactants, 8 on my products. And then my oxygens, I have 10. And then I have 6 plus 4, I have 10. Okay, so you just want to make sure that your reaction balances out first. Now I'm going to start with my given, and notice I'm given moles of my starting. Okay, my question is how many grams of carbon dioxide are formed? Everything else can kind of disappear. Okay, so my given is 1.65 moles of propane. C3H8, okay? And that's going to burn, and you're going to go to carbon dioxide. So the first thing that I want to do is I want to use my mole ratio. That's the only way to go from one substance to another is with my mole ratio. So moles of C3H8 go on the bottom. Moles of carbon dioxide are going to go on the top. For every 3 moles of carbon dioxide, I have 1 mole of C3H8. And I like to cancel as I go so that I can keep track of my units that I'm using. The next thing is I'm going to go to my mass by multiplying by my molar mass of carbon dioxide. So that's something I need to find. So I'm going to go from moles of CO2. So now moles of CO2 go on the bottom, and grams of CO2 go on the top. So molar mass, I have 12.01 plus 2 times 16.00. That's going to be 32 plus 12, so 44.01 grams. Okay, remember, I would like for you to multiply by the hundredths, or go to the hundredths place when you are using molar masses. So what you're going to do here is make sure that you have your calculator around you. 1.65 times 3 divided by 1 times 44.01 is going to end up giving me a value of 217.8495. I'm going to round to significant figures, 3 significant figures in my given. So I'm going to answer to 3 significant figures. Going to give me 218 grams of carbon dioxide. Okay. If 61.6 grams of propane were burned, how many moles of water were produced? Okay, so I've got 61.6 grams of propane. So my propane is C3H8. Okay, so the first step here, I can't use my mole ratio because I'm not in moles yet. So I'm going to put grams of C3H8 on the bottom for every 1 mole of C3H8. Okay, and then I'm going to multiply by my mole ratio. So I've got my molar mass here, and my mole ratio is going to be here. Okay, so I've got 3 times 12.01 is going to give me 36.03 plus 8 times 1.01 is 8.08. And when I add those together, I get 44.11 grams. So 44.11 grams. And then I'm going to look at my balanced chemical equation. My balanced chemical equation had, for every 1 mole of C3H8, I had 4 moles of H2O, because my question is how many moles of water. Okay, everything else can be crossed out. Okay, moles C3H8 cancel. I get 61.6 divided by 44.11 times 4 ends up giving me 5.586034.913. I call those obnoxious answers. You want to round to the correct number of significant figures. I have 1, 2, 3 significant figures here. So I'm going to round to 5.59 moles of H2O in this situation. Okay. So what if we have to go all the way? We have to go from mass of one thing, so say mass of A to mass of B. Okay, we'll do 3 steps always. So let's look at our chart. In this case, we started here. We started at mass. Now, each arrow, remember, represents a conversion factor. So I've got 1 arrow, 2 arrows, 3 arrows. So when I'm going from mass to mass of A to mass of B, I'm going to convert from mass of A to moles of A. Then I'm going to use my mole ratio to go from moles of A to moles of B. Then I'm going to use my molar mass to go from moles of B to mass of B. Now, something that I really like about this diagram, and I got this from Mr. P's chemistry page, I really, really like that he is showing that you can go from volume of a gas or particles to moles, and then use your mole ratio, and then go to particles. You can go to mass, or you can go to volume. You can go to all of these different places. This is something that is definitely worth spending some time to write it down. Pause the video and write it down. So our next example question is, what mass of oxygen gas is required to react with 12 grams of propane to form excess water and carbon dioxide? So if I'm looking at this, I have my propane reacts with oxygen to produce CO2 and H2O. Remember, I had this reaction right here. So I have 12 grams of propane to form excess water and carbon dioxide. I want to know what mass of oxygen gas is required. Okay, so I'm going from my grams of propane is my A, and I'm going to moles of propane to moles of oxygen to grams of oxygen. And sometimes I do this just so I can map it out for myself so that I really understand what I'm doing. So I start with my 12 grams. That's my given. Always write your given first, C3H8. And I'm going to convert to my moles of C3H8. So I'm going to put grams of C3H8 on the bottom. And we said that was 44.11 grams. Okay. And then I'm going to moles of C3H8. I'm going to cancel grams, and now I'm at moles. So now I want to multiply by my mole ratio. Moles of C3H8 on the bottom, moles of O2 on the top. For every 1 mole of C3H8, I have 5 moles of O2, or I need 5 moles of O2. That's going to cancel. And then my very last step, I'm going to go from moles of O2 to grams of O2. So when I'm dealing with O2, 1 mole of O2 has a mass of 32 grams. That's the molar mass. So I'm going to cancel that. And I'm going to go ahead and calculate. So now I'm just going to pull out the numbers. 12 divided by 44.11 equals times 5 equals times 32 equals. So if you're looking at this, I'm taking just my numbers. 12 divided by 44.11 times 5 times 32. I'm just looking at my numbers there. I get 43.52754477, but I'm going to round to 3 significant figures. 43.5 grams of O2. What mass of water will be formed from 68.3 grams of oxygen? Okay, so I'm looking for mass of water. So I'm going to grams of H2O, and I'm going from grams of oxygen. So 68.3 grams of oxygen. Okay, now I'm going to set this problem up a little bit differently. I did this on the board last week. Maybe some of you liked this better. So you kind of partition like railroad tracks. Grams O2 goes on the bottom. Moles O2 goes on top, and I partition it. For every 1 mole of O2, I have 32.00 grams of O2. Cancel grams O2. I'm at moles O2. Moles O2 goes on the bottom, and I'm going to moles of H2O. Well, I had 4 moles of H2O produced for every 5 moles of O2. Moles O2 cancel, and now I'm going to go from moles of H2O to grams of H2O. The molar mass of H2O is 18.02 grams for every 1 mole. Moles H2O cancel. And now again, I'm just looking at the numbers. I want to check to make sure that I end with the correct units. And I did, grams H2O. Now I want to multiply and divide by the correct numbers. So 68.3 on the top, 4, and 18.02 on the top. All those multiply and then divide by these two numbers, 32 and 5. Okay, so when I put that into my calculator, the way I go in order. 68.3 divided by 32 equals times 4 divided by 5 equals times 18.02. It's exactly how I plug it into my calculator. I'm going to answer in 3 significant figures because that's what I'm given. 30.8 grams of H2O in this problem. Okay, so here's another set of practice problems that we can look at. We have 4.6 moles of H2. If that reacts, how many moles of N2 are there? Well, let's go ahead again and balance this reaction. I put a 2 here and a 3 here. 4.6 moles of H2. And I'm going to how many moles of N2? So moles N2 goes on the top. Moles H2 go on the bottom. For every 3 moles of H2, I end up using 1 mole of N2. So 4.6 times 1 divided by 3 equals 1.5. I answer to 2 significant figures because that's how many are given in my problem. 4.6 is 2, 1.5 is 2. And that's my full answer. How many moles of N2 are needed in order to produce 25.4 grams of NH3? So I'm looking for moles N2. This is a mass to moles to moles. So 25.4 grams NH3. I'm going to put grams NH3 on the bottom. So that's going to be my molar mass per every 1 mole of NH3. So that's going to end up giving me 17.04. That's my 14.01 plus 1.01 times 3. Okay, grams NH3 cancel. And then I'm going to go from moles of NH3. And I'm looking at moles of N2. Well, for every 1 mole of N2, I have 2 moles of NH3. Moles NH3 cancel. So I do 25.4 divided by 17.04 equals divided by 2 equals 0.745. 0.745 moles of N2. And then finally, if 4.2 grams of N2 react with an excess of H2, so we can cross that out, just means I have more than enough hydrogen, how many grams of NH3 are produced? Okay, so I start with my given, which is 4.2 grams of N2. I'm going to divide by my molar mass, 28.02 grams of N2 for every 1 mole of N2. Grams N2 cancel. Now I'm going to go from moles of N2, which are on the bottom, to moles of NH3. Remember, I have to go to moles before I'm able to go to grams. So 2 moles of NH3 for every 1 mole of N2. Moles of N2 cancel. But I'm not where I want to end because I want to end at grams. So I'm going to multiply by my molar mass. 1 mole of NH3 is going to have a mass of 17.04 grams of NH3. Moles NH3 cancel, and I'm going to multiply all of that out. So 4.2 divided by 28.02, it's divided by because it's in the denominator, equals times 2 equals times 17.04 equals. So that's going to end up giving me a value of 5.10835. So 5.11 grams of NH3. 5.11 grams of NH3. I hope that this was helpful. If you have questions, which I'm sure you're going to have questions because it's not the easiest thing in the universe, you can watch some other tutorial videos online. You can reach out for some extra help for tutorial, or you can reach out during our class meetings.